let's start our fifth session on turbulence modeling course. So I hope you could study the previous materials because sometimes if you just don't follow the materials week by week, session by session, you will lose everything. So uh, I strongly advise you to study these materials uh, just when you finish one session and do not put it aside. So you remember we were talking about the nonlinear dynamic systems and this fact that these systems are subjected to sensitivity to initial condition was first demonstrated by meteorologists. One of them was Edward Norton Lawrence, and back in 1960s, he was trying to solve very simple ordinary differential equations (ODEs) uh, that he set in a computer just to predict the weather pattern. So he was doing simulations and he was getting time variations of, for example, velocity, temperature, humidity, and things like that. Then, by pure accident, he realized that if he restart his simulation, he's getting different data after a while. And although everything, I mean, the input file, the initial condition, and etc., everything was the same, but he was after restarting simulation, uh, he realized that if he waits long enough, the same simulation produces totally different results. And by that time, he didn't really understand why, and that was the starting point that people understand the sensitivity of nonlinear equations to initial conditions. And it was due to the precision in the machine or in your PC. If there are little perturbations, if you specify perturbations related to your actual numerical values and the point after that, for example, if the wind velocity is 10 meters per second, so it is not exactly 10 point, for example, 0.00000 infinite number of zeros. So there will be some digits because of the machine accuracy. So there might be some number 2 in here, for example. So those little digits, this is a very small number, but these little digits eventually are able to generate different solutions after a long enough time. And this is one of the problems that we cannot predict the weather. So these meteorologists generally solve uh, reduced versions of Navier-Stokes equations. So it's not something specific to us engineers. They also solve Navier-Stokes, but the reduced versions of Navier-Stokes to predict the weather. And those are not capable of predicting what is going to be the exact temperature, humidity, pressure, or, for example, wind level 100 years from now. Initially, you may think it is impossible. It would have been possible if you knew the exact conditions with exact values. If you cannot input those, and of course, boundary conditions are also a problem, it's not possible to predict the weather. So how do we predict the weather today then? Uh, we have a lot of satellite data. We have low fidelity simulations. What do I mean by low fidelity? It is written as lo-fi. So you you might seen hi-fi in somewhere. So we have low fidelity and high fidelity. What is low fidelity? Low fidelity means a low fidelity simulation means simulation with some noise and imperfections. So in some sound systems, you see this hi-fi. It means that there is a very low noise and imperfection inside in the sound that the device uh, produces. Your speaker, for example, if it is a hi-fi speaker, there is a small amount of noise. So the simulation that is low fidelity, it means that the simulation that has some noise and imperfections. So we have these low fidelity simulations. We combine these with the satellite data, and we look at statistics, for example, for the past 100 years, and we say, okay, it's most probably going to be 20 degrees 3 days from now. We still say most probably. So we are still not sure. As a human being, if you knew all the conditions of all human being in the world, and all the non-humans and the weather patterns and blah and blah and blah, let's say if you knew absolutely everything, you would know that who are going to, for example, uh, bump into your room, uh, and who is outside the room right now at the moment, or for example 10 days from now. So in turbulence we cannot predict instantaneous variables, but in engineering systems we don't have to predict instantaneous variables. That's the beauty of engineering. If we only can calculate somehow average variables, for example, average velocity fields, average pressure fields, average temperature fields, we can still design machines that are working with those. Therefore, we need to understand what kind of tools in terms of statistical analysis we have to use to analyze the instantaneous data. So we are going to talk about these tools. This will be just a short review on random variables and review of probability and statistics. So still, we are right now in the fifth session, and we didn't talk anything about turbulence. So in a perfect statistical sense, when we say u, this u, okay, which is our velocity field, for example, when we say u is a random variable, uh, it is inherently unpredictable, okay? So for a random variable in a statistical sense, it is first of all inherently unpredictable, and a particular value of u cannot be predicted, but its statistical properties can be predicted. So it itself is unpredictable, but its statistical properties that we are going to talk about, all these statistical properties today, are predictable. Again, giving the weather example, you may not predict the exact value of wind velocity 10 minutes from now, but you may estimate the mean value of wind speed. The question is, how do we do this? Basically, when we start with the word random, we will categorize random variable as a stationary random process, or a random process as a stationary random process, and non-stationary random process. So again, we categorize these stationary random process as ergodic and non-ergodic processes. So what are these? I will give some examples what actually they mean when we apply them to fluid flows. So you could have a simple jet flow, as you see in here. There is a jet that is coming out, and a flow is being issued on a turbulent jet. And what you could be doing at a certain point, uh, which is within the boundary of the jet, inside the boundary of the jet, you are recording one component of the velocity. For example, you're recording component u1 of the velocity. Let's say uh, you're recording it with a hot wire or whatever. When you plot the variation of velocity, this is the plot of variation of velocity u1 uh, with respect to time. So this is the time in seconds, for example. In here you have a time. Let's say you're recording for 100 seconds. So when you plot it, uh, it could look like this measurement, something like this that I called it first measurement. Then suppose that you go back to your home, and the next day you come again, and the probe that you were taking data is still there, and at the same point, and this point is point X with the vector sign. So you record for a second data set, and you will get a different looking random variation. So this second measurement is completely different than the first measurement. Let's say you keep repeating this uh, for n number of times. Okay, so uh, this is first measurement, this is second measurement, and this is the nth measurement. So every time you're getting different variation of velocity. And suppose that for the next 2 months, every day you come and record the velocity field at the same point, this same point X, for the same amount of time, for 100 seconds, for example. And each time you measure, you will get a different variation. Let's say I measured it 1000 times, so my n will be, let's say, 1000, and none of them will look like each other. This is what we mean by randomness. So none of them are looking each other. What I want to do now is to do some statistical analysis of data sets like this. So these are all data sets. So I'm getting all these data sets, and I can store it in an Excel sheet, for example. This could be a data of pressure. This could be a data of temperature. It could be concentration, etc. Everything depending on your application. My application here is just one component of velocity. So depending on data sets like this, we define some statistical tools. First of all, the ensemble average. What is the ensemble average? Ensemble average velocity at point x0 and at a certain time, let's call this time as t1, is equal to this equation. So what does it mean? Uh, u1 bar, first of all, bar denotes the ensemble average. Okay, the bar sign denotes the ensemble average. He said that this one denotes your location in the space. This one denotes the time that you are getting the average, and it's equal to limits of averages. So what are these averages? These averages are the values of velocity at the same point, at the same time, but at different let's say, uh, measurements. So these are the measurements that you did from 1 to n. And we said that in here, for example, we did it 1000 times. So in here, I goes from 1 to 1000. So this is the fundamental definition of ensemble averaging. What exactly do we mean if we have all these data collected? These data, as I said, we have all of them collected and keeping them in a hard drive. We select a certain, for example, time. So this is my certain time. This time, for example, in here I have selected 20th second. Okay, 20th second. So for example, what I got from the data sets for the first measurements, the velocity at t equal to 20 seconds is equal to 0.9. For the second measurement, again at the same time, 20th second, the velocity is 952. And for the last measurement, I got n equal to 3.81. These are all examples, okay? So we select a certain time, t1 equal to 20 seconds. This is marked in red dot. And for example, I got this table for n uh, number of measurements. We get the mean value of all of these velocities, and it is our ensemble averaging at that point in the flow field and at that instant of time. Okay? So the average of all of these numbers in the velocities is called the ensemble. You have to notice that we are not doing a time averaging. So these, for example, these orange lines, horizontal lines for each measurement denotes the time average value. So you notice that this is not the same as ensemble averaged. Time averaging and ensemble averaging are related. These two are related, but they do not have to be the same. Mathematically, we want this n number of measurements as large as possible. So theoretically, it should go to infinity to obtain what we call as a converged statistic. Okay, so for a converged statistics, this should go to infinity, but in a more practical sense, when we do experiments in laboratory, n is a large number. For example, for hot wire measurements, it could be tens of thousands. For PIV, particle image velocimetry measurements, it could be several thousands. So depending on what kind of average you want, the average of only velocity, or you want to average, for example, kinetic energy as well, and that makes a difference in the number of n. This is how we perform the ensemble averaging process. Depending on ensemble averaging process, we define a second statistical property, which later we will see that it's very useful function to understand the spatial geometrical structure of turbulence. And we call it autocorrelation function. So what is autocorrelation? A correlation is a measure that shows the extent to which two or more variables fluctuate together. For example, you can consider uh, a company's expenditures will likely increase if its revenue goes up. So, like this. That is a positive correlation. So, one is increasing, the other is increasing. On the other hand, you can have a negative correlation. So this happens when one variable increases as the other decreases. The more time, for example, you spend at work, the less time you have to spend with your family. So this is a negative correlation. Autocorrelation So we just said this is the correlation. So what is autocorrelation? Autocorrelation is a mathematical representation of the degree of similarity between a given time series or a given signal and a lagged version of again itself over successive time intervals. It is the same as calculating the correlation between two different time series, except that the same time series is used twice, once in its original form and once in the lagged one or more time periods. We generally use capital R like this. It is autocorrelation, so the velocity u is correlated with itself. So u means velocity is correlated with itself. This has a numerical value. So it is whatever this numerical value is, it does have some physical meaning as well. So at point x0 again, it has a value. So you can determine the value by this formula. If you go to another point, if you go from this point to another point, it can have a different value. Therefore, it will be a function of point, first of all, not only the point, it will be a function of time, the same with ensemble averaging so far. The autocorrelation is also a function of time plus this tau. What is this tau? This is the lag time. Okay, we said that it is shifted or it is lagged. This is the lag time. So what is I in here? The I is any instant. In other words, I is your measurement. So I is equal 1 for the first measurement, I is equal 2 is the second measurement, and so on. So just keep this definition in mind. For example, I'm going to give you the same measurements of the velocity inside the jet. Those measurements that we were talking about, the ensemble averaging at time equal to 20 seconds. Now I want to find the autocorrelation function at the same point. So point is the point x0. So my t1 is 20 seconds, and um, if I select tau equal to 2, it means that I am shifting the signal, each signal. So first measurement signal, for example, I will shift it 2 seconds. And then again, I have to shift the second measurement signals for 2 seconds. So for each one, I can calculate um, the autocorrelation value. For example, for the first measurement, the autocorrelation will become something like this number in here. So I just calculated, so don't worry about the calculation. I got two different values. So for the first measurement and for the second measurement, and then for all the measurements, I can obtain uh, the autocorrelation value. Then you need to average all of these, because you see there is the averaging operator in here. So if you average all of these, again I have to use a large number of samples. So n should be very large, theoretically goes to infinity, to obtain a converged statistics. So I got a numerical value for autocorrelation at the end. The question is this: what if I choose another tau value? So let's say a tau value which is very large. 2 seconds, I chose 2 seconds in the previous calculation, and 2 seconds is close to the original data. So I have 20 seconds, and then I chose 2 seconds. The question is which of the two points would be more correlated with each other? Is 20 seconds and 22 seconds, or for example, the thing that I'm writing in here is 20th seconds and 22 seconds are more correlated, or 20 and 82? Can you answer?
I guess the first option is more correlated.
Yes, the closer you are to the original point, they would be more correlated. So if you just think about it, two closer points, quantitatively, it means that the number you get has a higher value. So this, in general, the autocorrelation is a number between -1 and 1. So as you decrease this tau value, you will get higher and higher correlation. This autocorrelation value is actually a quantification of how these points in signals are correlated with each other. As you just guessed, as you increase tau, then uh, your uh, correlation level drops down.